Hey, good morning, everyone. We should start hopefully right on time because we have a quite tight schedule today. Uh, for the general audience, please write your questions throughout the talks, and then I will read them and at the end of the talk. Regarding our lectures, I just want you to know that we are recording the talk, so if anyone doesn't want to do that, so please let me know. And this is pretty much for all of us. So I will just start the first session of today, plasma session, and I want to say a few words about the speakers. Two of the speakers are not able to participate even virtually, so they had sent me their presentations, which I will run from my own computer, but we won't have questions. And one of them is our first speaker, the keynote speaker of today's session, which is Jakub Krasik. Professor Krasik is the head of the Plasma and Pulse Power Laboratory at the Faculty of Physics at the Technion. He's an APS fellow and just received this year also the IEEE fellowship, as well as the NPSS Chris Christensen Award for contribution in experimental nuclear and plasma science. His talk today is research of underwater electrical explosion of wires and strong shock waves generation. This short presentation will present the main physical phenomena accompanied and governed underwater electrical explosion of wires of both architectures of a single and arrays, and the application of the generated strong shock waves for studying of high energy density matter will be also shortly discussed. So I will just start Professor Krasik talk.
Thank you, Chairman, for opportunity to give this talk, which has titled Underwater Electrical Explosion of Wire and Wire Range Generation of Stroke Shockwaves, which we are doing for more than 10 years in our Plasma Physics and Pulse Power Laboratory in Technion, together with our PhD students, which are listed here, and my colleagues and friends in our laboratory and around the world, which are also listed here. First, I just will remind that wire electrical explosion is a very fast change in physical state of metals as a result of intense energy input due to pulsed current. And current densities could be extremely high. Main parameters are listed here. And I want to only emphasize that we are talking about extremely fast phase change in the matter during explosion of wires. The very good recent review by Reshkin and Bakht one can find in EA Transaction Plasma Science, recently published on wire explosions in vacuum. However, we are doing this research using underwater electrical wire explosion, which has many advantages as compared to explosions in vacuum or gas. These advantages are listed here: high breakdown voltage of water medium, which allows us to avoid parasitic plasma formation, which is almost unavoidable in the case of wire explosion in vacuum or gas. And high pressure of adjustment water layer also help us to increase even more this breakdown voltage. Using these advantages, we can keep high resistance and high resistance of water to compression. We have very slow wire radial expansion. Therefore, we keep high energy density deposition into the wire. Radiation is almost negligible in our case because of so-called bath effects, as I will show you later. And also due to slow radial expansion, magnetohydrodynamic instabilities does not have time to be developed. In our research, we are using both experimental and simulations. we are using in experiments 3 types of generators in our laboratory. This is microsecond timescale, sub-microsecond, and nanosecond timescale generators, with parameters are listed here. And thus, in different timescales and different energy density rate deposition, we can study this interesting phenomenon. In research, we are using different diagnostics: electrical, optical, photomultipliers, fast diodes, time and space results, visual spectroscopy, and recently photonic Doppler velocimetry. This experimental research is accompanied by magnetohydrodynamic and hydrodynamic one dimensions and two dimensions simulations. Main equations are written here, and these simulations are coupled with equation of states, Ohm law, and using different conductivity models. And of course, for each of these simulations also coupled with the electrical circuit of our generators. Typical streak image of the explosion wire one can see here in microsecond time scale. This is just, you may see here, exploding wire and strong shock waves, as well as expanding in radial direction and discharge channel. This is frame image, which showing rather uniform form of the wire, exploding wire, and detached from the wire strong shock waves. Almost the same results were obtained in nanosecond time scales. Here you just see typical image, a streak image of the exploding wire and the generated shock waves, and in upper you may see the current, discharge current, and resistive voltage. So from this early data, we already learned that radial explosion of wires does not exceed 10 to 5 centimeters per second, which is almost hundreds of times smaller, slowly than the radial explosion of wires in the case of vacuum for the same energy density depositions. Below you can see a table with main parameters of the explosions, and I would like to emphasize that we can achieve extremely high energy density deposition, up to hundreds of electron volts per atom, which is also impossible to achieve in the case of wire explosion in vacuum or gas, because of the parasitic plasma channel formations and fast expansion of the wire. Now, first we have questions: is really we do not have plasma channel formation? How stable is our exploding wire for hydrodynamic and magnetohydrodynamic instabilities, thermal instabilities, which are accompanied by strata formation? Research of the time results spectroscopy where I was involved showed us that indeed we did not see any signs of the H alpha, H beta spectral lines in the vicinity of the exploded channel. And this gives us evidence, confidence that with accuracy of around 5 microns, there is no plasma channel formation in the vicinity of the wire. By doing some simulations, we obtained that in the vicinity of the wire surface, the water is still phase trajectory, is showing us that water does not going to boiling point because of very high pressure in this region. Regarding magnetohydrodynamic overheating instabilities, I just shown you here two expressions which show us that the time of development of this instability strongly depends on the density, because the larger the density, the larger is the time. Because in our case we have extremely high density, 10 to 12 and more particles per centimeter cubic. In our case, even in microsecond time scale, there is no time for magnetohydrodynamic instability to be developed. regarding overheating instability, we obtained this instability finally using synchrotron radiation from Grenoble facility. This is very nice, bright radiation beam, and with space resolution down to 8 microns, we were able to see it. Here you may see the strata formation typical for overheating instabilities. And on the right side, you see magnetohydrodynamic simulations, which predicts appearance of these instabilities in microsecond time scale. However, the wavelength of this instability does not exceed tens of microns, and therefore there is no large influence on the global resistance of the exploding wire of these instabilities. Very interesting question was regarding radiation of the wire, because it was assumed that wire radiate as similar to black body. Our research, time-resolved spectroscopy, here you may see the spectrums at different times, showed that indeed at the beginning of wire explosion as well as the end of wire explosions at a longer time duration, we can fit obtained spectrum by black body curve. However, during the explosions, there is no way to have a fitting, and we have very large deviation between experimental and simulation data. The reason of this is that when wire reaches temperature of several electron volts due to radiation in the tail of Maxwellian distribution, Planckian distribution, we have ionization of the water in the vicinity of the wire. When I am saying in the vicinity, I mean 1-2 microns, not more. And here we create a rather large dense plasma with density 10 to 12, 10 to 21 centimeter per cubic. This plasma has absorbed the radiation of the wire, and part of this radiation is re-radiate towards the wire. We call this as so-called water bath effect. So what we obtained in experiment during this high temperature phase is the radiation from the boundary of this thin wire layer. Important question was is the efficiency of the energy transfer to water flow. We used two methods, shearing interferometry and ballistic methods. These experiments, which was also coupled with simulations, showed us that efficiency can be extremely high, up to 22% of the storage energy, deposited energy into the wire, which can be about 80% of the total storage energy can be delivered to the generated water flow. And in this delivered energy, about 25 is going to potential energy of water flow, I mean compression, and 75 respectively percent going to kinetic energy of water flow. It was a dispute in community what is the most efficient explosion of wires, over-damped or under-damped discharges, which later characterized by ringing of the discharge current. We did a few experiments, and here you may see typical streak image of the shock waves and expanding wire. And using this data for different type of the discharges, we obtained that indeed over a damped discharge or almost critically damped discharge, as you may see here according to shock velocity time dependent evolution, is the most efficient one. This discharge characterized by a very extremely fast energy density deposition to the wire, allowing wire to expand with velocity even a little bit exceeding than 10 to 5 centimeters per second. We did several experiments trying to obtain if indeed we can gain more energy deposited to the water flow using, for instance, aluminum combustion of aluminum wires. In earlier research, everybody claimed that aluminum combustion can be released only in tens or hundreds of microsecond time scale. However, when we are exploding wires at such extreme high current energy density, 10 to 8 amperes per centimeter square, we obtained using time result spectroscopy bands of aluminum oxide. And these bands, this is a strong sign that we have combustion of aluminum. Indeed, looking for shock velocities, which is generated by aluminum wire array, this is on the right graph, you can see it. You see that in the case of 50 microns and 50 wire planar wire array wires, one obtains that first decrease as it's expected of the shock velocity in the vicinity of the wire, but however later on we obtained increase in the velocity, and this could be only due to additional energy deposition by the combustion of the aluminum. I would say that underwater wire explosion is a unique method for studies of phase transition. Example of this you can see here. This is also strict image of the exploding wire, and first you may see weak shock waves, which accompanied phase transitions of the first kind when material change its volume, and only later there is a main explosion with generation of strong shock waves. Using this time when one obtains weak shock waves and calculating the energy using electrical data from current and resistive voltage drop, one can compare this data with existing tabulated data and to see if there is agreement between them at such extreme conditions of the energy density deposition. We also did experiments for comparison of the existing equation of states and conductivity models with our experimental data. For instance, conductivity values were obtained by fitting simulated current and voltage waveforms to experimental data, and pressure values were obtained by using fitting simulated wire expansion to experimental data. It was a long run experiments with different wires with very broad range of parameters of the density, temperature, and pressure. As a result of this research, I would say that only in microsecond time scale we have obtained rather good correspondence between experimental and data and existing equation of states. Mainly we used CSEMI database. However, going into sub-microsecond and nanosecond time scale, we see rather large disagreement, and it was necessary to correct conductivity models and equation of states to get good fitting with experimental data. Now I will move for cylindrical and spherical shock waves implosion. This is very interesting, exciting research. Indeed, what you see here, for instance, a cylindrical wire array consisting of several wires. During the explosion, each wire generates its own shock waves. After that, these shock waves, individual ones, overlap each other and form one cylindrical imploding shock waves. And below you may see how it's going on in experiments for several wires. Using so-called self-similarity method, when one assumes that shock waves already does not feel piston, in our case this is exploding wires, one can calculate pressure behind the shock wave front using these expressions which I presented here. It's evidently that for cylindrical implosion, for spherical implosion, one can gain much larger pressure behind shock wave front as compared to the cylindrical shock wave. The main question in this research was, is strong shock wave keeps its uniformity during propagation? In our experiments, for instance here typical scheme of experiments with 100 kilovolts, 760 kiloamperes, 400 nanosecond generator, and you see wire array, cylindrical wire array consisting of 40, 60 copper or aluminum wires with very small diameters. You may see also voltage and current waveforms which showing you close to critically damped discharge when almost all energy stored in the generator is deposited to the wire, and streak image of the exploding shadow streak image of the converging shock wave. Now, using different methods, for instance, here you may see multi-frame images of the convergent shock waves, and when this cylindrical convergent shock waves approaches the axis of implosion, we obtain very bright light due to extremely high temperature and pressure which is created in these locations. Pressure can go up to 1 megabar or even 2 megabar, depending on the stored energy or deposited energy into the wire array, and temperature of several thousands of kelvins. In the case of spherical wire array, we managed to design these setups. Here you may see an external view of wire arrays of 40 or 60 spherical ones, and as I said, one can expect much higher pressure in the vicinity of implosion region as compared to the cylindrical wire arrays. Doing these experiments, we also obtained critically damped discharge, as you may see here, and very strong light emission from the origin of the implosion, which appearance depending on the wire array. In the table, I just showing you that according to hydrodynamic simulations, which were coupled with equation of states and which were based on the time of flight of the shock waves, which we have obtained experimentally and deposited energy into the wire array, one can expect to obtain in radius of 5 micron close to the implosion origin pressures of tens of megabars with density significantly larger than 5 times larger than normal density and temperature of several tens of electron volts. The state of the water, actually this is already not water, this is plasma, with pressure more than megabar can exist tens of nanoseconds, which I am showing here in the plot for microsecond and sub-microsecond time scale of experiments. Thank you very much for your attention, and I would like to say that right now we're continuing this research, and we see that this method can be used very efficiently, much more efficiently than other methods for acceleration of targets and for compression of targets, isentropic compression of targets with efficiency maybe tens times larger than those which people are using when they apply magnetic pushing. Thank you again.
Okay, so while virtually giving the applause to Professor Krasik, I would like to introduce our next speaker, Professor Moron from Weizmann Institute. Professor Moron is the head of the plasma laboratory at the Faculty of Physics at Weizmann Institute. He is an APS and an IEEE fellow. Today's talk is experimental determination of the thermal and turbulent ion motion in a stagnation plasma by describing the recent advantage in spectroscopic diagnostic methods developed for measuring the true ion temperature and the discrimination of the turbulent motion in the Z-pinch stagnation plasma. This work presents experiment and simulation that contribute to the understanding of ion thermalization and stagnation and further investigation of turbulence at stagnation stage. So Professor Meron, please take it from here.
Yeah, thank you very much. Good morning. Are you hearing me?
Yes.
Okay. So we are continuing the high energy density that Yasha was talking about, but it's high energy density of another, solid. It's a plasma which is really can be very dense, above solid density or lower than solid density, and very hot. So this is still high energy density, but it is another problem. And the problem is measuring the ion temperature. Now, the ion temperature is, it's one of the most important, maybe the most important parameter to measure, because it's really the ion temperature that determines the radiation, because through the electron heating and of course the fusion. And most of the results I will discuss today will be were part of the PhD thesis of Dror Alumot, a lot of help from Eyal Krupp and Evgeny Stambulchik and others, and the high resolution crystals that we are using that are very high resolutions are from University of Vienna. Okay, so, we work on Z-pinch where we form a hot and dense plasma on the axis as the pinch is produced. And this is where we demonstrated the method I will be talking about. And the idea is that particles are accelerated radially. And then what we want them to do is to come to the center of the cylinder, and after being accelerated, to collide and to produce heat. The heat will go to the ions. The ions will have to give it to the electrons if we want radiation, or the ions have to keep it for themselves in order to make the fusion. Okay, so therefore there are Z-pinches with deuterium to produce neutrons and things like this. Okay, so really until maybe 8 years ago, or maybe 9 years ago, people believed what I just said, that if you take a Doppler profile of any ion from stagnation, then this Doppler will give you the entire ion temperature that you reached at stagnation. And this was very widespread and believed by everyone. However, we made spectroscopy at the Weizmann, and we were suspicious that that's not the case. And the first study that brought this up was a PRL in 2011 by Krupp et al., where we showed that if you really measure the entire Doppler, it is not at all the ion temperature, it is a lot of hydro energy. And actually the ion temperature is much lower. And this is the experimental system. I discussed the resolution. It's X-ray spectroscopy. It's very delicate, accurate measurement, and that I will have to skip. And then just to show you a piece of data from that experiment, this is a line which is a singlet. It is not opaque, it is thin, it is a satellite, it's not a resonance line. And therefore the broadening, the shape is determined only by the Doppler velocity. There is no stark here. And therefore this line gives you exactly the total ion kinetic energy in the system. And then it was proven that this ion kinetic energy that you get from this Doppler broadening is really, this is in a way a difficult problem to really discriminate what part of this is temperature and what part of it is turbulence. So what I'm showing you is how you get the entire amount of ion kinetic energy, but I'm not saying now how you discriminate between the two. It was done in this work of 2011, but I want to go to our recent work, which was published in 2019, so I'm skipping the details here. Okay. Here what you see, this is something that I'll show you later, that this turbulent kinetic energy, the hydro energy, you can measure it and you can see the dissipation, dissipation of it. It still doesn't mean that you know the ion temperature, but you can study the dissipation of the ion, of the hydro energy. Okay. In this work, the ion temperature was found to be low, but I'm skipping the way it was done. And the dissipation time of the hydro is 2 nanoseconds. It can be measured. Okay. So this is something for theoretical work that we have been doing with the Princeton recently. So now regarding what I want to discuss now, following that measurement of 2011, we were looking for a method that is direct method to measure the ion temperature. And to the best of our knowledge, there was no direct method like this until today. And this method that I will show you was employed at the Weizmann, developed and published. And we think it can fit also much larger high energy density experiments that of densities of 10 to the 24 or 10 to the 25. And of course, lower 10 to the 21 as was done in this experiment. And I will tell you what is this, which we think unique and direct method that to the best of our knowledge, the only direct method we know for measuring TI. Well, you know, the idea that Stark broadening is used only for density, usually everyone knows that. But the trick of this method, which took a lot of time to find, is the following. The ions, when they, you know, in the plasma, produce electric fields on the emitters. And one can look at indirect way on another effect. And the ions can be correlated together because of moderate coupling. Now, the fact that if ions are correlated, they affect the electric fields around any emitters, this is known, but no one was thinking that this can be used to measure the ion, actually, because the coupling is a function of the ion. And even if one thought about this, probably he would think the effect is small, and it is really small, and I will show it to you. So here you see line shapes for different ion temperatures which change the coupling. It means you have to work on a mode whether there is ion coupling. And you can see that the shape is a function of the ion coupling, which is of the ion temperature. And this is the spectroscopic system used for this one. It's 3 spectrometers looking at the same point of the Z pinch. Each spectrometer is high resolution. Actually, each spectrometer sees only one line because it's very high resolution. And I will show you the data. So I will give you some time for questions. And this is the data. You can see lines that are imaged along the column. And the lines have intensities, they have a spectral shape, they have broadenings. And then you do the analysis. And the analysis is the following. You can see that the shape of the line is a function of the electron density with something called the triplet line ratios, which was used for the first time at NRL maybe 20 years ago for another purpose to measure electron density. I mean, you get the measurement from one line, the other line processes, transport the processes in the plasma. Okay, here you can see now the physics of it. When the Doppler temperature decays, it dissipates into ion heat. The ion gives the heat to electrons, and the electrons give to radiation. Now, if the ions give the heat to electrons very fast, so the temperature of the ion will be this green one, which is really low, because they always get from the turbulence at the dissipation time, the turbulence wants to dissipate. And this, as I said, this is another theoretical work. And they lose it quickly to electrons because of electron-ion collision time. So this is very important. And actually, the 2 PRLs of 19 was consistent with 2011. But as I'm saying, the method of 219 can be operated in other systems too. So this is, I think I showed this already. And this is a slide which really gives the physics that when we are accelerating the plasmas, we want them to dissipate into heat. That's what we want. But it doesn't work like this. At the beginning, we set up turbulence in any stagnation. And then the turbulence goes to the ion heat. And therefore, the ion temperature will be lower than what we think. And then the ion will give it to electrons. If the system allows this, you will get radiation. If you don't want radiation, you prefer that the ions will keep their heat and do it in a fusion. This is my last slide here. This is the work I described with the Princeton, whether when you know that there is turbulence, then you can go to turbulence models and there are density fluctuations in turbulence. And therefore now you can say, okay, I want to analyze all my spectroscopic data again, but with fluctuations of densities, which turns out to be in our case of about factor 2 by different models. And you see that it is really nice that the radius of the plasma, which I didn't mention, is also measured and was also fit to the data in our PRLs. But when you fit it to the data, when you take into account the fluctuations of density in turbulence, then it turns out it fits to the data much better. And so therefore, this data can be really used not only to study the turbulence, the dissipation of turbulence, ion temperature is very low, and so forth, but to even study the properties of turbulences. So this is what I would like to say. I will show you the summary. Do I have a half a minute to say the summary, or?
Yes, you may. Yes,
okay, so the summary is that this can be in NIF explosions, in big Z pinches. You know, you develop turbulence during the implosion, but what is proven here that at stagnation, that's what's important, a lot of kinetic energy of the ion is stored in turbulence, in hydromotion, and therefore the ion temperature is not something that you can conclude very easily. If you try to conclude it from various measurements like amount of radiation or things like this, you may get errors because you assume various assumptions on the plasma, on its density, on its size, and you can get wrong numbers for the ion temperature on which you will make a lot of conclusions that will be misleading. Really measuring the ion temperature is very important because it gives you quantitatively the right number that is going to play a role in the radiation and the fusion. As I said, the discrimination between temperature and hydromotion, this is a very basic issue in fluid dynamics, very important in high energy density plasmas in particular. And the dissipation of the hydromotion is also important to study, and that's what we do. And okay, regarding plasma rotation, I am not touching it in this talk. So thank you very much for your attention and for inviting me to give this talk. And if you have any questions, sure.
So again, thank you very much for this interesting talk. We do not have we don't have a lot of time for questions, but I don't see anyone that has written any questions in the Q&A. So we'll probably move on, and thanks again for this interesting talk, and probably a discussion will be offline. Okay, so our next speaker is Dan Lev from Rafael. Again, as I mentioned, some of our speakers aren't able to participate directly, and Dan is one of them. So again, I will introduce him and then operate his talk. Dan is a senior engineer in Rafael, specialized in space electric propulsion. He conducts research in aerospace engineering, plasma physics, and experimental physics. In particular, he works on development of low pressure Hall thrusters and hollow cathodes. Today's talk is from plasma science to space electric propulsion. In this talk, a brief outline of the most recent successes in the development of plasma-based space propulsion system in Rafael will be presented, with a view of future trends, opportunities, and challenges in this rapidly growing field.
Hello, my name is Dr. Dan Lev. I'm from Rafael, Israel, and I will present on the plasma science and space electric propulsion that is conducted at Rafael and in general in the world. Today I will talk first about the plasma and electric propulsion devices. I will dive a little bit into the basic physics, that we see in those electric propulsion devices that we use both at Rafael and around the world. Then we'll go through the current developments that are conducted at Rafael. And of course, we'll finish with a little glimpse into the future global trends of plasma devices. Electric propulsion devices are known for a few features when it comes to plasma physics, a few features that characterize them. So first of all, we talk about a relatively dense plasma in the order of 10 to the 16th to maybe 10 to the 19th meter cubed. So this means that these plasmas, along with the fact that they're fairly cold, the electron temperature of 1 to 10 eV, they're highly collisional. And this is something that we want in these kind of devices, of course. We would like to achieve high degree of ionization in those devices. And in the next slide, I will talk a little bit about how those devices work and how they accelerate the plasma. But what you should know is that this plasma eventually becomes singly ionized and almost fully ionized when it exits the thruster. And once it goes through a set of electric and magnetic fields, it creates momentum, or thrust, as we call it in the space industry. Now, the gases that are used in these kind of devices are mostly noble gases like xenon, krypton, and argon, but also other types of gases like H2, and in some cases even hydrogen is used, or ammonia, or other types of gases. But I can confidently say that xenon is probably the most used gas for these devices. Now, I should add at this point that in space currently there are hundreds of these devices operating. I think that we actually crossed the 1,000 accelerators or thrusters operating in space this year. So these devices are quite abundant, and they're highly required to perform all kinds of space missions. So how do they work? Plasma devices are quite straightforward. There is gas injected into these devices. The gas is ionized through collisions in most cases, because plasma is highly collisional. And after we achieve a sufficiently high degree of ionization in the thruster, that plasma goes into a set of electric fields, sometimes also magnetic fields, and these electric fields accelerate the ions that were generated within the plasma. These ions produce the momentum, eventually the thrust that propels the spacecraft. And we should never forget that once we eject those ions out of the propulsion device, we also need to neutralize them. So we have to have some device, which is called the cathode neutralizer. It is just an electron gun that is used to eject electrons that eventually neutralize the ions that are being ejected from the thruster. Now, you can already understand that we would like to have as dense of a plasma as we can, so very high plasma density, coming out of the thruster in the electric propulsion world. I can identify three main challenges that are being encountered in the past decade, and there are a few more that are tackled almost every year. So the main one is probably plasma wall interaction. Plasma wall interaction between the ionized gas, which is accelerated, so it obtains energy of up to about 300 electron volts, and in some devices even more than that. These ions, when they hit the walls, the inner walls of the thruster, they erode those walls. So there's a very, very important research that goes into all the interaction between those 300 eV ions, mostly xenon ions, which are heavy, So they carry with them a lot of momentum, and the interaction between these ions and the wall. Now, the walls in these devices are made out of ceramics or graphite, which can withstand much better than metal, for example. They can withstand charge erosion or ion erosion. There is also the need to achieve sufficient ionization at low power. So as we go to low power, we also go to low density in these devices. So collisionality goes down. If collisionality goes down, this also means that ionization level goes down. So the plasma is no longer fully ionized. It might be strongly ionized, but each one of those neutrals that does not get ionized also does not produce thrust. At best, it will get heated up by heavy collisions and will produce some thrust, which we also call cold thrust. But there is a need to ionize as many neutrals as possible in order to accelerate them and generate thrust. At the same time, we don't want to doubly or triply ionize them because, as you know, doubly or triply ionizations just cost more and more energy as we move along in the ionization levels. So this is something that we would like to avoid. So there's a sweet spot that needs to be found in these thrusters. And another challenge that is encountered is the design of efficient neutralizer. So our neutralizer, which we call the cathode neutralizer, it is just an electron gun, but it has to be lightweight and use very little energy because we're going to send these devices into space where it is very costly to send more mass and energy is very costly onboard spacecraft or satellites. So we need those plasma electron neutralizers to be very light, to be able to ignite and produce the ions almost instantaneously when we ignite the thruster, and they're supposed to be able to work for thousands of hours without any malfunction, right? We cannot change these devices in space, so it's very important to understand these. In terms of the devices that we're working on at Rafael, we're working on Hall thruster technology, which is one particular type of electric thruster, plasma thruster. It looks exactly like you see in the middle picture here. Very bright, very, very nice. You can see on the side here the cathode neutralizer, which can be either on the outside of the thruster or in the center. And we're using mostly xenon as the propellant in these devices. Xenon just because it has a very good ionization energy to mass ratio, which means that we won't have to pay high energy costs in order to be able to accelerate 1 unit of mass. Now, the thruster is not the only thing that is designed and developed at Rafael. Since we are delivering at Rafael full systems, ideally we would design full systems and be able to market and sell them. So the thruster is just part of the deal. We also need a power supply unit, which is usually very costly because it's a space power supply unit. It's supposed to work in space where there is radiation, high degrees of radiation. And there are also other devices like propellant management assembly, valves, propellant tanks, flow controllers, pressure regulators, and so on, that are also part of the system. And they're used to be able to regulate the xenon flow or the propellant flow into the thruster. And these devices are very important. And they also carry quite a lot of weight. So there is a whole orchestra of devices that are being developed at Rafael in order to be able to produce and sustain these systems. So the most important system that we have currently is operating in space. It's called the R400 Electric Propulsion System, or EP system. It operates on board the Venus satellite. It operates at throttling power range, which means the changing power range between 300 and 600 watts. The mission originally was supposed to work 5 years in space. It was actually launched in late 2017. But since it worked so nicely, it was decided to extend the mission. So currently, we're already more than 3 years into the mission, and the mission is going to be prolonged by at least 3 more years. I think it's going to double. So that's the we have in space, and the system is composed of not only the R400 Hole thruster that you see here, but also the power supply unit that supports it, the propellant tank that carries the xenon used in the mission, and then the flow controller and xenon heater and thruster valves, everything that we need in order to regulate the flow into the thruster. We're also currently working on the R200 Hole thruster. The R200 Hole thruster is a low power Hole thruster, basically the younger brother of the Venus thruster. It operates at around 200 watt, and it's still under qualification, but it's under pretty advanced stages of qualification, and we expect to launch this system in the next few years. The thruster uses a low current cathode neutralizer, which we call the ARC-1A. 1A stands for 1 amp. It operates at discharge current, which is quite low, 0.3 to 1.2 amps. It uses relatively low mass flow rate. In xenon, 0.1 milligrams per second correspond to about 1 SCCM of xenon. The ignition voltage of the cathode is less than 400 volts, and we already proved this cathode to work for longer than 4,000 amp hours. So this is the cathode that serves the R200 thruster. The same thing with the higher power version of the Hole thruster. We call it the R800 just because the nominal power of this thruster is about 800 watts. This Hole thruster is also under development, slightly behind the R200 thruster. But the good thing about this thruster is that we implemented many features that are quite advanced in Hole thrusters. So you can see here that the cathode moved from the side to the center, which is very important to reduce the footprint of the entire thruster. You can see that the thruster can operate not only on xenon, but also on krypton, which is much more cost effective than xenon. So it's a bit more advanced thruster. We also have the cathode to go with that thruster, which is the bigger brother.
Sorry for that.
Of the ARC-1A thruster, so it operates at roughly double the current of the other cathode and carries roughly the same features. We also developed the power supply that supports all of these systems. So the power supply can support either one of the 3 thrusters that we showed you, so anywhere between 100 and 900 watts. It can support the cathode, all kinds of cathode neutralizers. It has a relatively high efficiency, which is very important. It means that 91% of the power that goes into the unit is actually delivered to the thruster, to the propulsion system. And it has internal full redundancy. So if one of the power supply or power units goes out, there is one to replace it on spot in space, which is very important to increase the reliability of the unit. And we constantly are working on new systems that are, or new power supply units that are lighter and more efficient. In terms of infrastructure, I won't dive into all the details of our infrastructure, but you can imagine that there are many vacuum chambers that are involved here. Our biggest vacuum chamber is the one that we're using for entire system experiments, or just the Hole thruster experiment. And this system can go. This chamber can go down to pressure levels of the high 10 to negative 8 torr, And while we inject the gas and operate the thruster inside, it can go up to about 1.5 10 to negative 5 torr at maximum mass flow rate. So that's actually pretty impressive. We also have 5 chambers just for the cathode neutralizers. Now, I'd like to move a little bit into the future global trends in electric propulsion and plasma devices, just to give you a really quick overview of what is entailed us in the future. So number one is mass production. More and more satellites are launched every year. We need to produce many devices, many systems, and many thrusters. So we need to move to mass production, like cell phone production. We are moving to low power just because the satellites are becoming smaller and smaller. The systems should be more cost effective, very cost effective. So we're moving to very cheap systems. Systems that used to cost $1 million per system might go down in price to less than an order of magnitude lower than that, so less than $100,000. And this is why many clients, many satellite companies prefer quantity over quality. In terms of future trends, I will really just slightly touch each one of those lines. Field emission electric propulsion, so different types of electric propulsion where higher electric fields generates more efficient plasma. Low work function materials in order to be able to emit more and more electrons at lower temperatures, especially for the cathode neutralizer, and erosion resistant materials to be able to withstand the erosion that the ceramic channel undergoes. So, to summarize, I've shown you that Rafael has a whole set of plasma propulsion devices, all developed in Israel. And I can tell you that Rafael is a known player these days in the field of plasma propulsion and space propulsion in general. Innovation is the key. So finding good ways to make more efficient and lighter and more cost-effective devices. And there is a really fast changing trend or rapid changes that are taking part in the global scene. And these changes make us be, we have to be more flexible over time and be able to keep up with the pace. Thank you very much for listening.
Okay, so we are a little bit behind the schedule. So I would like to ask Gaia Feingold to start her talk about numerical investigations of ammonia, oxygen, helium, ignition limits in non-thermal plasma. Please, Gaia.
Hi, that's me.
Yeah.
Okay, can you see my screen?
Yes. Go ahead. Yeah, you can start.
Okay. So this is a talk on plasma-assisted ammonia ignition. So it's more about chemistry in a plasma discharge. It's a numerical investigation of ignition characteristics of ammonia, oxygen, and helium mixtures in nanosecond pulsed non-thermal plasma. The first question is, why are we interested in ammonia? And that's because it's a renewable fuel, it's carbon-free, and potentially it's zero emission. So this is a report from last month. It was commissioned by the Getting to Zero Coalition, which is a coalition which includes the Global Maritime Forum, the World Economic Forum, amongst others. And it was looking at a path to achieving zero emission shipping. It compared few different fuels, amongst them ammonia, methanol, biofuels, hydrogen, and synthetic diesel. The top two fuels that came up on this comparison were green ammonia and green methanol. And as you can see on the fuel production end, ammonia wins because it has the strongest long-term scalability. And green methanol is held back because it requires a carbon feedstock to procure. And the carbon capture energies are really not there yet. And on the vessel end, methanol wins because you can burn it in existing engines. And ammonia requires dual fuel combustion engines, which are not there yet, again, so it requires more development. But the bottom line of this report was that ammonia is most likely to be the long-term and large-scale solution. So looking at the combustion qualities of ammonia, ideally it produces just nitrogen and water. So the production of it itself is just water, air, and renewable electricity. So it can be very cheap to produce. There's no carbon in the combustion, and it makes use of excess energy and existing infrastructure. The bad part of it is more the combustion process itself. It has high NOx emissions. It has a low flame speed. It's resistant to auto-ignition and forced ignition, and it has narrow flammability limits. So all of this is what makes it incompatible with the existing systems. With a plasma discharge, the chemical processes can be enhanced and solve precisely all of these problems. In this research, we focus on the ignition problem, so the ignitability and the narrow flammability limits. How does plasma affect ignition characteristics? So it does it by, there are different paths, but the paths that we're looking at for ignition are the ones that have to do with the species. So you get plasma-generated species, OH radicals, and excited species such as excited oxygen, other species, and fuel fragments, which all accelerate ignition. You can ignite at shorter residence time and alter ignition delay. You can ignite at lower temperatures and leaner mixtures, which is widening the flammability limit. And if you add enough of these radicals and species and sustain them, then you can have completely stable combustion and ignition at all temperatures. So we built a plasma ammonia combustion kinetic model. It's comprised of three main parts. The first part is excitation and ionization by electron collisions. So these three are well-established databases. Then we have excited species reactions. It's comprised of different models that we found. The first is an ammonia synthesis model. So it's hydrogen, nitrogen, and ammonia. It was developed by using experimental plasma characterization under atmospheric pressure. So it's not completely validated, but it is based on experimental data. Helium, some additional helium, ammonia, and oxygen ammonia reactions, and the helium oxygen submodel, which was experimentally validated for methane combustion. And finally, we have neutral ground state reactions. This is a combustion model, which we chose because it had best overall performance for both flame speed and ignition. What we did with this model was look at the effects of a nanosecond repetitively pulsed discharge. This discharge provides and sustains the species that we're interested in to enhance ignition. In this study, we look at the frequency and the number of deposited pulses and their effect on the ignition delay time and how they shorten ignition delay time. And we look at the effect of the frequency on the minimum temperature that we can reach for ignition. This is for widening the ignition limits, and it's important for cold start and for flame stability in engines. We do this using a zero-dimensional solver, which combines two chemistry solver. One is ZD Plaskin for plasma, and the other is ChemKin2, which is a chemical kinetic solver. So the first batch of simulations is looking at the effect of the pulse repetition frequency and the pulse number on ignition delay time. We have a stoichiometric mixture of ammonia and oxygen in 75% helium. We chose helium for this because it's simpler to model than nitrogen, and it's a validated submodel. The mixture has an initial temperature of 1500 Kelvin at a pressure of 1 atmosphere. This is so that the mixture ignites thermally without a discharge, and we can compare the discharge to just the thermal ignition. The energy per each discharge pulse is 0.0 millijoules per centimeters cubed. This is a low energy for each pulse to avoid heating effects. the reduced electric field is 180,000. It's adjusted again experimentally, and the pulse width is 1 to 3 nanoseconds, and this is adjusted to keep the energy constant as we have an increasing temperature. Commercially available pulsars. And finally, the pulses that we deposit, we increase up until ignition. So eventually we have a continuous case for each of these frequencies. On top of that, we have a comparison to thermal ignition. So we take the initial pulse temperatures, which is 1500 Kelvin, and we add on to it delta T. And the delta T is what would happen if we take the energy instead of pulsing and use it just to heat the mixture. So we have a higher initial temperature. So now looking at the results, on the x-axis, we have ignition delay time. So starting at high and going down. And on the y-axis, we have the number of pulses and also the deposited energy, which is saying the same thing. Eventually. We can see that for lower frequencies, we can get a 40 to 60% reduction. And then if we go to very high frequencies, we can deposit much more pulses before ignition. And also we can get a reduction of up to 90% of ignition delay time. So this is in this end. And we can see that there is always an improvement when comparing to just heating the mixture. So plasma always does better.
1 minute, please.
Yeah. I have 1 minute?
Yes.
Oh man. Okay, I'll just get to the conclusions, I guess. Which is that the pulse discharge is faster. You can get a faster ammonia ignition. The deposition is more effective than instantaneous heating, which is what we just showed. The part that I skipped is for higher pulse repetition frequencies. You can get shorter ignition delay times for the same energy input. For ignition, you can get ignition at lower temperatures, which is extending the flammability limits of the mixture. And for very high pulse repetition frequencies, you can get ignition at all temperatures. And right now we're working on experimental validation of the chemical model, so building a plasma reactor, and we're extending the model to include nitrogen also, which is more complex but more relevant to engines. That's it. Thank you.
Okay. So thank you very much for this carbon-free future fuels. I'm sorry, but we don't have time for questions, and so we will move on to Amnon Fruchtman talk about mass separation by oscillation, electromagnetic field. So Gaia can stop sharing. Amnon, please go ahead.
Are you hearing me?
Yeah.
Do you see the PowerPoint or the PDF?
Not yet. Not yet.
Do you see it now?
Yeah, great now.
Mass separation?
Yeah, we see it. Great, you can start.
Okay. I'll make it full screen. I hope you still see it.
Yep.
Okay, so the subject is mass separation by oscillating electromagnetic fields. It's a very important subject for applications. And the idea is to use just electromagnetic fields with a specified phase difference between the oscillating electric field and the oscillating magnetic field. It can be used in principle. It's of interest for isotope separation, of separation of particles for spent nuclear fuel. I will start with the mechanism itself. The mechanism itself starts from the very basic case. Assume you have an oscillating electric and magnetic field. So you see here the electric field and the magnetic field. And I'll take one example, which is particles, waves that are circularly polarized. So the electric field and the magnetic field have constant in time amplitude, and they move circularly. Here in this description, you see the magnetic field is into the page, and the waves go counterclockwise, what we call left-hand circularly polarized field. And we define here the phase. Phi is the phase between the electric field and the line perpendicular to the magnetic field. So I can imagine case that the phase is just zero, which in this case, the electric field and the magnetic field are perpendicular to each other, and other case where they are parallel or anti-parallel. If they are parallel, the phase is pi over 2. If they are anti-parallel, like in these drawings, it's minus pi over 2. Now, where do we have such things? We can just take electrodes and coils and generate these kind of phase between them. But when we have waves, this phase, phi equals 0, characterizes traveling wave. While when you have phi equals plus pi over 2 or minus pi over 2, this is typical for standing waves. This is something very basic that we learn at first year in the university, but sometimes we miss it. So this is how the relation between the electric and magnetic fields are. This kind is of relation between this phase also characterizes evanescent waves, but I will focus on standing wave. So if we write it, the electric field and the magnetic field, this is how they are written with the phase, but instead of just looking into the formal description, you can just remember this picture, which tells you what are the waves. So we can solve the equations of motion of a charged particles with these fields when I assume first that these fields are just time dependent, but they are uniform in space. Later, for the calculation, I will take into account the spatial dependence of the waves. But just for a beginning, I will calculate the solution with uniform in space. And it's actually possible to find analytical solutions. And these are the velocities of the charged particles as they depend on the various parameters. What we have is a wave with a frequency omega, and the omega naught is related, it's the cyclotron frequency associated with the uniform axial magnetic field, while omega 1 is the cyclotron frequency associated with the oscillating magnetic field. And also there is a component here, which is coefficient, which depends on the intensity of the oscillating electric field. And this is the solution. Phi, what you see in blue is when the case of a traveling wave, and cosine phi is 1. What you see in red is when phi is plus pi over 2 or minus pi over 2. So in the usual case of a traveling wave, the velocity is described here. In the other case, when you have a standing wave, which is the important thing in this talk, we have these red solutions. So what can we see? Here, what you see here is this term shows actually what is called ion cyclotron resonance heating. Usually when ion cyclotron resonance heating is used is for heating particles. There is a resonance layer in a non-uniform magnetic field, and particles gain energy while they cross the resonance layer. But for mass separation, we use a uniform magnetic field, and therefore the particles see all the time they can stay in resonance, and this is used for mass separation by heating specific particles. So this term is responsible for this. However, if we look at in red now at ion cyclotron resonance, we see that also for a standing wave, we have also this ion cyclotron resonance heating, but instead of being bounded, as here because of the sign, it's bounded. When it's standing wave, the heating is unbounded. So in principle, you can get a higher ion cyclotron resonance heating. However, this is not the main point of this talk. The main point is this term, where you have mass selective axial pushing. So you see here first that you have a velocity that increases in time. It's a secular term. You can increase in time the velocity. But more important is that the velocity is not necessarily in one direction. It depends on the sign of this coefficient. In my notation, omega naught is negative and omega is positive. So this term can be either positive or negative, and depending on the sign, it determines whether the pushing is in one direction or in the opposite direction. So you can tune the frequency so that it is between the two cyclotron frequencies of two particles of different mass and cause them to move in opposite directions. And this is the main point. So I'll show you, this shows again in purple, you see, pardon?
3 minutes, please.
Okay, so the main point is here. You see here the secular goals. So what I will show here is how you can separate two isotopes.
יורם, אני באמצע איזשהו הרצאה כאן.
Please mute your phones for the participants.
Can I continue?
Yeah, continue. Just please mute all other.
Okay, so lithium-6 goes to the right here, and lithium-7 goes to the left by picking the correct part values. One question is how to generate in a plasma such waves. So the good candidate is Alfvén waves, which have frequencies smaller than the cyclotron frequency. And actually one has to tune and select waves in a multi-species plasma where the dispersion relation is more complicated. So this I leave for as a challenge to do. And the second thing is not just Alfvén wave, but standing wave. In this numerical example, the wavelength is 4 meters, and these are the parameters of the waves. It is very similar to what at Kurchatov they use for ion cyclotron resonance mass separation. These results for lithium shows also taking into account collisions, which are one major problem, ion-ion collisions, which will disturb this mass separation, and also the initial velocity. So here you see, if they start at rest and no collisions, there is no problem. One go to one direction, one to the other. But here, I allow each species to go in the wrong direction initially. But because of the force, the mass selective force, the force reverses the direction of each one, and as we want, lithium-6 goes to the right and lithium-7 goes to the left. And here is the standing wave. All this picture is for 1 meter between -1/2 and +0.5 meter. This is 1 meter, a quarter of a wavelength where this happens. If we can actually take all the wavelengths or even more, and divide this device into cells of quarter wavelengths. Here we put a wall, And from both sides, if you take the signs correctly, lithium 6 goes here, lithium 7 goes also from the right and from the left, accumulate on this collector. While 1 meter away, there is another collector, 1/4 of wavelengths, which collects lithium 6. So here you can have a device made of various cells, and in each cell, each wall collects preferably particles from what we would like them to do.
Please conclude, Amnon. We need to conclude.
Pardon?
Please conclude the talk.
Okay, so there is another example of spent nuclear fuel, which I will not go to it. And this is a device, a way to use Alfvén wave, standing Alfvén wave for separating particles. It's a challenge to design the waves appropriately and to overcome the challenges, which are collisions and initial ion velocity, which one has to fight against. Thank you.
Thank you very much, Amnon, for this talk, but we must go on. I see that people are chatting, use the chat box throughout, which is wonderful, so please feel free to do so. But we need to move on to John Leopold talk regarding a split cathode as a novel type of neutral electron source for relativistic magnetron. John, please begin. Amnon, can you please share your screen? Thank you. Amnon, can you unshare your screen with the options in the Zoom?
Okay.
Thank you. Thank you. So, John, are you with us? Yeah. Please go ahead. John, we're not hearing you at the moment. Can you please check the John? Can you please check while sharing the screen? There is a box of sharing also sound. We do see the presentation, but we cannot hear it.
He's on mute.
Yeah. Just a second. Okay, thank you. John, you are on mute session now.
Morning.
Oh, okay, great now.
The electron current carried by a magnetized annular beam of radius RB, propagating in a conducting tube of radius R, is space charge limited, and its value is given by this formula. ILC depends on the energy of the electrons, EV, and on the ratio between the tube and beam radii. 17 kiloamp is the Alfvén current. So when the beam flows from a tube of a given radius to a tube of a larger radius, it over-injects it. A virtual cathode forms, from where a return current flows upstream towards the source of the current. When you watch these strongly magnetized beams flow in terms of its charge density contours, you can hardly distinguish this. But look at the longitudinal generalized momentum phase space, where you can see the virtual cathode developing along a return flow with most of the space between the source and the tube's radius transition filled eventually by a low energy, higher density electron cloud. Here you can see the same thing in terms of the electron energy. The result of this dynamical process is known as a squeezed state, which is an electron cloud in a lower energy and higher space charge density state. This behavior gave the idea to Fuchs, Prasad, and Shamiloglu that such a squeeze state is an ideal electron source for a relativistic magnetron instead of a solid cathode, which suffers from the well-known problem of pulse shortening due to the explosive plasma formed on its surface, which expands and eventually shorts the cathode-anode gap. Here, this is achieved by two radius transitions in the outer grounded tube, and the squeeze state forms between two virtual cathodes. So another idea was put forward, a magnetic mirror-like scheme. When the axial component of the magnetic field increases from B1 to B2, the annular beam radius decreases from RB1 to RB2 as the square root of the magnetic field amplitudes. The decrease in the electron radius decreases the value of the limiting current, the effect of which is the same as changing the radius of the outer tube. This can be seen in the longitudinal velocity phase space a virtual cathode forms and partial squeezing is only seen, and the current is still ending on the anode wall. To return the entire current, Fuchs and Shamiloglu suggested that this can be achieved when the magnetic field is increased exponentially, and they suggested a design for their diffraction output magnetron, which does exactly that. So recently we came up with a different idea, a device we named a split cathode. A split cathode is a regular annular cathode with a reflector connected to it by a central rod. The potential of the entire structure is the same or almost the same, and the electrons emitted from the cathode slow down at the reflector from where they are returned towards the cathode. A potential well forms between the cathode and the reflector in which the beam oscillates. In phase space, you can see a similar picture as that seen for the magnetic mirror scheme, only that current does not flow downstream, and some current leaks upstream. More squeezing is seen here compared to the magnetic mirror scheme, but squeezing here is also only partial. We verified this scheme experimentally. The experimental setup includes a 12-stage Marx generator attached through a vacuum chamber to the experimental tube, a solenoid providing an axial magnetic field of 1 Tesla is wound around the experimental tube. A 1 millimeter diameter hole in the reflector samples the electron beam contained in the cathode reflector gap and is measured in a Faraday cup. The split cathode is a hard ionized black surface to avoid surface damage or unwanted emission. The connecting rod is screened by the electron beam and does not itself emit. The emitter consists of 20 hollow carbon fiber capillaries, and the cathode has a larger body to act as a partial reflector to the return current.
1 minute, please.
The voltage, about 150 kilovolts in the simulation, was adjusted to that measured in the experiment. When the reflector is not attached, the experimental and simulated currents are very close, about 400 to 500 amps. When the split cathode is used, the voltages agree, and the current is near zero. No current flows to the anode. The electrons oscillate between the current, cathode, and the reflector. The simulated current collected on the reflector oscillates at a frequency corresponding to the transit time of the beam in the cathode-reflector gap. The current measured by the Faraday cup through the sampling hole in the reflector confirms this. And so to summarize, the concept of a split cathode has been introduced. In a split cathode, a partially squeezed electron beam state forms. We have demonstrated this by simulations supported by experiments. Such a partially squeezed state, when used as an electron source or relativistic magnetrons, is advantageous because pulse shortening plasma is kept out from the interaction region. Thank you for your attention.
Thank you very much, John, for this talk. And we should move directly to our last speaker at this session, Marko Cevic, which will give a talk about the effects of plasma rotation in an experiment of magnetic flux compression by an imploding plasma.
Yes, thank you. Yes, hello, I hope you hear me. Thank you, Yoav. So as you can see, this work is a collaboration between authors of Weizmann Institute, of Naval Research Laboratory, Holon Institute, and Princeton University. With this slide, I want to show you our experimental principle in geometry. As you can see, we have a Z-pinch with pre-embedded axial magnetic field. As the plasma implodes, it picks up axial magnetic field and compresses it. The main difference of this geometry from standard Z-pinch is that during implosion, not only plasma is compressed, but also magnetic field, which carries a profound effect of on magnetic field distribution, on the pressure and energy balance, and the implosion dynamics. What we report here is that first time in a gas puff Z-pinch with BZ, a self-generated plasma rotation is seen, observed, and this plasma rotation has a velocity comparable to the implosion velocity and the rotation direction dependent on BZ. So this rotation has a profound effect on energy and force balance because of centrifugal force, and on mitigation of instabilities, which I will show. So to observe and to measure plasma, we designed the experimental setup shown on this slide. The uniqueness of our spectroscopic setup is that we are using 3 spectroscopic systems to look plasma at 3 different directions. The spectroscopic diagnostic setup is designed to acquire data with high spectral, spatial, and temporal resolution for simultaneous determination of self-generated plasma rotation together with all 3 spatial components of the magnetic field and plasma parameters. With this setup, we know the non-uniformity of plasma in theta direction. So shortly, System 1 is spectroscopic system 1 is used to measure plasma parameters and ion velocities, which means rotational and implosion velocity. System 2 measures azimuthal and radial magnetic field with also with rotation and implosion velocity, while system 3 is designed to measure BZ measurements from is designed to measure BZ from the dopant plasma. Fast imaging is simultaneously done with spectroscopic measurements. Now, the principle of rotation measurements is shown with this slide. So diamond rotation velocity measurement is based on observing the Doppler shift of the spectral line in opposite azimuths at the same axial location. The opposite signs of the Doppler shift at opposite azimuths indicate the presence of ion rotation. Now, to implement this principle, there are two problems that needs to be overcome. First one is that we have integration over line of sight. Oops, sorry. And for example, if I'm looking through the plasma shell, I can see many velocities belonging to different plasma section. Second problem is that plasma rotation occurs as the pinch implodes. So projection of implosion velocity to the line of sight also Doppler shifts spectral lines. Now, to overcome these problems, first, plasma is observed at the outer edge of ion spectral line intensity distribution, where only Doppler shift due to rotation is observed, as it's shown in this graph. The other problem is solved by using or taking advantage of radial separation of the charge states during the implosion, which allows us to do local measurements. This means that we can determine the radial distribution of the rotation velocity, B field, and plasma parameters without the need of Abel inversion. Now, plasma rotation, as I said, is affecting the plasma dynamics in two ways. The first is that it's affecting force balance throughout the implosion, and the second is it's providing shear stabilization of plasma instabilities. So the importance of measuring plasma rotation velocity is that we can now calculate centrifugal force, not here F cent, and compare it to the other forces detected on plasma. So detailed measurements of plasma rotation simultaneously with all three components of the magnetic field and plasma parameters enable us to calculate radial force balance for the first time. We compare forces due to the cross product of JZ and B theta, which is the inward pinching force, and we compare it to the outward forces due to the thermal gradient, which we can calculate thanks to the temperature measurements, force due to the BZ counter pressure, which we can calculate due to the BZ measurements, and of course due to the centrifugal force, which we calculate based on rotation velocity measurements. And these rotation here show just a sample of this detailed data showing radial distribution of rotational velocity and of magnetic field. From these measurements, we constructed a table. And from this table, for example, you can see that at approximately at minus 130 nanoseconds before stagnation, the centrifugal force is quite large, and it's about 50% of the pinching force. At later times, some of outward forces is equaling the pinching force, and as the implosion proceeds, actually these forces stop the implosions. So this all means that centrifugal force has a significant role in Z pinch implosion and stagnation. Also, this detailed data could help benchmark present-day MHD codes. The other way the plasma is affecting the rotation is affecting plasma dynamics is through mitigating of instabilities. So it's known that rotation can affect the effective acceleration during the acceleration phase, or it can also mitigate instabilities by phase mixing of instability perturbation. So if we adopt the stabilization mechanisms given in the paper of Schumlack in 1995, and if we adopt it and calculate it to our condition, we get to this condition. Analyzing the data, we see that this condition is almost satisfied for our experiment. So rotation indeed can mitigate MRT instabilities.
1 minute, please, Marco.
Yes, thank you. So the other phenomena is the phenomenon of iso rotation, which is found in collaboration with researchers from Princeton. So basically what iso rotation means is that MHD system wants to rotate at the same frequency, and this iso rotation can explain the observed rotation dynamics, that we see that rotation is deaccelerating near the cathode, which is counterintuitive. And iso rotation is the novel observation never before observed in Z pinches. So as a conclusion, to summarize, plasma rotation has a significant influence on plasma dynamics, affecting force and energy balance and mitigating instabilities. Iso rotation is a new effect, and it gives us a new possibility of using Z pinches to study astrophysical phenomena such as accretion disk. And we believe that present-day MHD codes can be benchmarked by this detailed data. Thank you for your attention.
Thank you, Marco, for this talk. And with this, we conclude the morning session of the Plasma Science. I would like to thanks again all the speakers, and hope to have fruitful discussions with the chats later on. So we meet again for the after the break for the parallel sessions at 1:30. And thanks again for all the speakers and the participants.